On October 29th, 2025, a mysterious event took place behind the Sun, which had profound implications. For 2 weeks, every telescope on Earth went blind to what was happening in the vastness of space. When observation resumed, a massive sunspot, one of the largest in the past decade, had appeared, pointing directly toward our planet. Meanwhile, the interstellar object, DRI Atlas, discovered earlier in the year, was steadily approaching its closest path to Earth, set to reach it on December 19th, 2025, at a distance of 269 million kilometers. And remarkably, the sunspot, 90% the size of the one that triggered the Carrington event in 1859, might rotate back to face Earth at the same time. 3I Atlas reaches its closest point. While coincidence is one possible explanation, there are 8 other theories that science cannot easily dismiss. Tonight, we dive into the events that unfolded during the hidden window behind the Sun. We'll also explore why a Harvard astrophysicist is raising questions that no one wants to address, and what the convergence of these two phenomena might mean for everything we have built as a civilization. The data is real, the timing is highly suspicious, and the next 2 weeks could prove to be the most significant period in modern history. Before we begin, take a moment to like and subscribe if this science-driven, calm format resonates with you. If you're able, hit the hype button in the comments. Let us know where you're tuning in from, the current time at your location, and the key question this topic raises for you. I will be addressing the most insightful comments, either in this video or in a follow-up. On October 29th, 2025, at precisely 7:47 a.m. Eastern Time, something slipped behind our Sun. The interstellar object designated 3I Atlas, which had traveled across the vast void between stars, reached the closest point in its trajectory to our Sun, a mere 203 million kilometers away. And at that exact moment, every telescope on Earth went blind to it. This was no malfunction. It was a result of geometry. A phenomenon known as solar conjunction occurs when an object passes behind the Sun from our perspective, placing our star directly between us and the object in question. The glare from the Sun becomes absolute, and the Sun's corona bleeds light in every direction. For nearly 2 weeks, 3I Atlas was in a state of total invisibility. Let's pause and think about that for a moment. The third interstellar object ever detected by human instruments, an ancient traveler that entered our solar system from the vast, empty space between stars, chose this specific trajectory out of billions of potential paths, and at the precise moment of its closest approach to the Sun, it was hidden from our view, inaccessible to human observation. Now, 5 weeks later, something else has captured our attention. A massive sunspot complex has rotated into view on the Earth-facing disk of the Sun, designated AR4294, R4296, and R427, O200, O205. This complex represents one of the largest active regions observed in over a decade. Its magnetic classification Beta, Gamma, Delta marks it as one of the most complex sunspots in solar cycle 25. This sunspot is capable of producing X-class solar flares, and it is 90% the size of the sunspot that caused the Carrington event in 1859, the most catastrophic geomagnetic storm in recorded history. 2 events, one hidden and one revealed, both converging on Earth in December 2025. The question we will explore tonight is not whether these events are connected. Science cannot definitively answer that question just yet. The question is simpler and far more unsettling. What are the odds of this happening? Let's begin with what we know about the hidden window. 3I Atlas was first discovered on July 1st, 2025, by the Asteroid Terrestrial Impact Last Alert System Atlas telescope in Chile. Within days, Astronomers realized that this was no ordinary object. The object's velocity was too high to be gravitationally bound to our Sun, meaning it would pass through our solar system only once and never return. This made 3I, Atlas, only the third confirmed interstellar visitor in human history. After Oumuamua in 2017 and comet 2I, Borisov in 2019. However, 3I, Atlas, stood out from its predecessors in several key ways. First, its speed at discovery was approximately 137 km/h, faster than either of the previous interstellar objects. By the time it reached perihelion, the closest approach to the Sun, its speed had increased to around 153 km/h. The object was also ancient, with estimates placing its age between 7 and 11 billion years older than our own solar system. But the most intriguing aspect of 3I, Atlas's trajectory, was its path through our solar system. The object passed within tens of millions of kilometers of Mars. It approached Venus, and it came close to Jupiter. On December 19th, it will reach its closest point to Earth at a distance of 269 million kilometers. These planetary alignments are statistically unusual, and Harvard astrophysicist Avi Loeb calculated the probability of this exact trajectory occurring by chance at approximately 0.5 or 1 inch 20. Ling, ling, ling. What makes 3I Atlas even more remarkable is not just where it went, but when it went there. Perihelion, the closest approach to the Sun, is a critical moment for any object in our solar system. It's when gravitational forces are strongest and velocity is highest. For any spacecraft, this is the optimal moment to perform what physicists call an orbit maneuver. The slingshot effect, or gravitational assist, is a well-understood principle of orbital mechanics. In simple terms, a high-velocity maneuver at perihelion is more efficient than the same maneuver at a lower velocity. If 3I, Atlas, had any capability to harvest solar energy, perihelion would have been the moment of maximum power. But that moment was hidden from us. Now, consider the counter-argument. Some may claim that the solar conjunction of 3I, Atlas, was merely a consequence of orbital mechanics and Earth's position in its orbit. Had Earth been on the opposite side of the Sun, we would have had a clear view of the object's perihelion passage. The timing, they argue, was merely coincidental. This is true, but it is also incomplete. The trajectory of 3I, Atlas, was determined long before it entered our solar system. Its path was set by its velocity and direction when it crossed the heliopause, the boundary where the Sun's gravitational influence ends and interstellar space begins. That crossing occurred approximately 8,000 years ago, before human civilization even invented writing. We cannot know the intentions of something that old. We can only observe the outcome. The outcome is this: 3I. Atlas performed its closest solar approach during a period of total invisibility from Earth. Any course corrections, any interactions with the solar environment, happened in a place where we could not see it. And then, as 3I, Atlas, emerged from behind the Sun in early November, something else appeared. The sunspot complex AR4294 through AR4298. Sunspots form through complex interactions in the solar magnetic field, processes that unfold over days and weeks beneath the Sun's surface. The timing of its rotation into view is striking. As 3I Atlas emerged from behind the Sun, the sunspot complex rotated into view. By late November, it had grown to one of the largest active regions observed in the current solar cycle. Correlation does not equal causation. This is the foundational principle of scientific reasoning, and it's important to hold firmly to that. But the timing of these events is undeniably curious, and we cannot ignore the possibility that the convergence of these two phenomena, one hidden, one revealed, may carry deeper significance. The Sun regularly produces large sunspots during periods of solar maximum, and solar cycle 25 has already exceeded predictions. With levels of activity not seen in over 2 decades, the appearance of a major sunspot complex in late 2025 is entirely consistent with the expected behavior of the Sun. However, it is crucial to note that normal solar activity does not usually coincide with the arrival of an interstellar object. Let me clarify what we are not suggesting. We are not claiming that 3I, Atlas, caused the sunspot. We are not suggesting that an alien intelligence manipulated the object to trigger solar activity. We are not asserting that the December convergence signals any coordinated threat. These are extraordinary claims that would require extraordinary evidence. And we do not have such evidence. What we are suggesting is simpler. The timing is unusual. The geometry is suspicious. The questions raised by this convergence deserve serious attention. Not dismissal. The mainstream scientific consensus holds that 3I, Atlas, is a comet. It has a visible coma, the characteristic fuzzy envelope of gas and dust that surrounds an active comet nucleus. Spectroscopic analysis has detected compounds like carbon dioxide, cyanide, and others commonly found in comets. NASA's official position, as stated in press releases and public communications, is clear. The object looks like a comet and behaves like one. While this consensus may be correct, it does not explain all the peculiar observations associated with 3I, Atlas. For instance, 3I, Atlas, survived its perihelion passage intact, which is highly unusual. The object passed through a coronal mass ejection (CME) in late September, exposing it to temperatures exceeding 500 degrees Celsius conditions that would typically cause a comet to fragment. Yet, its nucleus remained whole. Additionally, 3I, Atlas is glowing bluer than the Sun. During perihelion, space-based coronagraphs detected a color shift that would not occur if the object were merely reflecting sunlight off dust particles. The blue emission could indicate something other than reflected light, possibly gas molecules, or perhaps something else entirely. Moreover, 3I, Atlas exhibits an unusual ratio of nickel to iron in its composition. The gas plume surrounding it shows nickel concentrations far higher than typical for comets, and these ratios are more commonly associated with industrial alloys rather than natural substances. Each of these anomalies could have natural explanations, but when taken together, they form a pattern that has prompted Harvard astrophysicist Avi Loeb to rate 3I, Atlas, as a 4 on his scale from 0 to 10, where 0 represents a definitely natural object, and 10 represents a definitely artificial one. A 4 is not high, it's not a claim of alien technology, but it reflects genuine uncertainty. The data does not yet allow us to close the question, and so, we watch, we wait, and we gather more data. Meanwhile, the sunspot complex continues its rotation across the solar disk. In approximately 2 weeks, it will move to the far side of the Sun, temporarily reducing the threat of Earth-directed solar flares. However, sunspots can survive multiple rotations. R4294, one of the sunspot regions, could return around Christmas, once again facing Earth just as 3I, Atlas, reaches its closest point. On December 19th, the object will pass 269 million kilometers from Earth, its closest approach ever. During a time when we have the technology to observe it, the hidden window may have closed. But the questions it raised are just beginning to unfold. What exactly happened behind the Sun on October 29th? What is the relationship between the ancient interstellar traveler and the sunspot that appeared? As both events converge on Earth in the final weeks of 2025, what should we be watching for? The Sun does not answer these questions. The comet does not provide explanations, and the silence between them grows heavier with each passing day. In astrophysics, there is a concept known as the observation window. It refers to the narrow slice of time during which a transient event can be detected and studied before it fades or moves beyond the reach of our instruments. For I, Atlas, the observation window was interrupted at the worst possible time. We had tracked its approach for months, monitoring its increasing brightness, analyzing its spectral signatures, and debating its nature in scientific journals and social media. Then, as the geometry of our solar system shifted, a curtain was pulled across our view. What happened behind that curtain remains unknown. Space-based observatories tried to peer through the sun's glare. The Parker Solar Probe, orbiting closer to the sun than any spacecraft in history, gathered data from its unique vantage point, the SOHO satellite, stationed at the first Lagrange point between Earth and the Sun, captured images through its coronagraphs. The European Space Agency's JUICE mission, currently on its way to Jupiter, passed within 64 million kilometers of 3I, Atlas, on November 4th, and turned its instruments toward the object. The data from these missions is still being processed, and the analysis will take months. In the meantime, 3I, Atlas, continues its journey outward, growing fainter each week, but the sunspot remains. AR4294 sits on the solar disk like an unresolved question. Its magnetic field lines are twisted into configurations that store enormous energy. At any moment, these field lines could reconnect, releasing their stored power in a flash of radiation and a wave of charged particles. The probability of an X-class flare from this region remains elevated. The chance of something larger, approaching Carrington-class intensity, is low, but it is not zero. We live in a civilization built on electromagnetic infrastructure. Our power grids, communication networks, financial systems, and transportation all depend on the stable flow of electrons through copper and silicon. A sufficiently powerful solar storm could induce currents that our systems were never designed to handle. Transformers would overload, satellites would fail, and the cascading effects would ripple through every facet of modern life. This is not speculation. It is the assessment of engineers and physicists who study space weather. The question has never been whether such an event will occur, but when. And now, here we are in December 2025, watching a sunspot of historic proportions while an interstellar object of uncertain origin approaches its closest point to Earth. The hidden window has given way to a window of convergence. What we see through that window will depend on what we choose to focus on: the sun's wound, the comet's path, or something else entirely. For billions of years, the sun has marked itself with dark patches, temporary blemishes on a star that burns at 5. What happens next is still to be written, but the questions it raises are more urgent than ever. We call them sunspots, though the term scarcely captures their true nature. These are not merely spots on the sun's surface, they are wounds, fractures in the sun's magnetic fabric. These are regions where the internal pressure of twisted magnetic field lines breaks through the sun's photosphere, creating areas that are cooler than their surroundings. And while cooler is relative, the temperature of a sunspot is still high enough to vaporize any material known to human science. The sunspot appears dark only in contrast to the surrounding sun's blinding surface. The sunspot complex currently facing Earth is not just large, it is extraordinarily dangerous. AR4294 first emerged in late November as the sun continued its regular rotation cycle, which takes about 27 days to complete from our vantage point on Earth. By the time the region rotated fully into view, astronomers immediately recognized its magnitude. The area covered by the sunspot complex reached nearly 2.000 millionths of the visible solar hemisphere. To put it in terms we can comprehend, this sunspot complex is large enough to swallow Earth 20 times over. However, sheer size alone does not define its potential for danger. The critical factor is its magnetic complexity. The sun generates its magnetic field through a process called the solar dynamo, driven by the differential rotation of plasma within the sun's convective zone. Near the equator, the sun rotates faster than at the poles. This differential motion stretches and twists the magnetic field lines, winding them tighter until they become unstable. When these twisted lines break through the surface, they form sunspots. Simple sunspots have a bipolar magnetic configuration, with field lines arcing from one polarity to another like the poles of a bar magnet. These are classified as beta regions, and while they can produce solar flares, their energy release is usually modest. More complex sunspots develop additional magnetic polarities, creating tangled configurations where field lines from different sources interact. These are classified as beta-gamma regions. The most dangerous configuration is beta-gamma-delta, which occurs when opposite polarities exist within the same sunspot umbra, creating extreme magnetic stress. AR4294 has the beta-gamma-delta classification, making it one of the most dangerous sunspots observed in recent history. The energy stored in these twisted magnetic configurations is nearly incomprehensible. When magnetic field lines of opposite polarity are forced close together, they can suddenly reconnect, releasing their stored energy in a process known as magnetic reconnection. This energy accelerates particles to nearly the speed of light, heating them to tens of millions of degrees and producing electromagnetic radiation across the entire spectrum, from radio waves to gamma rays. This is what constitutes a solar flare. Solar flares are classified on a logarithmic scale. Class flares are common and cause minor effects. M-class flares are moderate and can disrupt radio communications. X-class flares are the most powerful, capable of causing radiation, storms, and widespread technological disruptions. Within the X-class category, the numbers continue to climb. An Shum flare is significant. An X10 flare is severe. The Carrington event of 1859, the largest solar storm ever recorded, is estimated to have been caused by a flare somewhere between X40 and X50. In the first week of December 2025, the sunspot complex AR4294 through AR4298 produced multiple class flares and several M-class events. On December 8th, the adjacent region AR4299, which had previously rotated to the far side of the Sun, announced its return with an X1 Noah flare. This was the same region that had produced a major flare in mid-November, including an X5-16 flare, the strongest of the year. The Sun has not been calm for months, and now, the largest sunspot complex of the current solar cycle is facing Earth directly. Let's consider what happens during a major solar flare in terms that illuminate the physics behind it. Imagine a rubber band stretched to its limit. The tension in the band represents stored energy. If you continue to stretch it, eventually it will snap, and all that energy will be released in an instant. Now, imagine billions of rubber bands, each one twisted and tangled with its neighbors, all stretching to their breaking point simultaneously. When one snaps, it can trigger others in a cascading effect, releasing more energy in minutes than humanity has used in its entire history. The solar flare itself travels at the speed of light. 8 minutes after the reconnection event on the Sun, the electromagnetic radiation reaches Earth. This radiation includes not only visible light but also X-rays and ultraviolet radiation, which ionize the upper atmosphere. On the daylight side of the planet, radio communications can be immediately disrupted. Airline pilots flying over polar routes may lose contact with ground control. GPS signals can become unreliable, but the flare is only the beginning. Major flares are often accompanied by coronal mass ejections, or CMEs, vast clouds of magnetized plasma. Billions of tons of solar material are hurled into space at speeds exceeding 2 km/s. Unlike the electromagnetic radiation from the flare, CMEs are physical objects that take time to travel the distance between the Sun and Earth. They typically take between 15 hours and several days to reach us, depending on their velocity. When a CME strikes Earth's magnetosphere, the effects can be both spectacular and devastating. The magnetosphere which is our planet's invisible shield generated by the churning iron core beneath our feet, deflects most of the charged particles streaming from the sun, but a powerful CME can compress and distort the magnetosphere, allowing particles to funnel toward the poles and creating the aurora phenomena. Under normal conditions, the aurora borealis and aurora australis are visible only at high latitudes, typically above 60 degrees north or south. However, during major geomagnetic storms, the auroras can be visible much farther from the poles. During the Carrington event, people in Cuba and Hawaii saw red and green lights dancing across the sky. In Colombia, near the equator, the night sky became bright enough to read by. The beauty of the aurora masks its potential danger. As charged particles interact with Earth's magnetic field, they induce electrical currents in any long conductor. Power lines become antennas, picking up currents from the sky. Pipelines develop voltage gradients. Train tracks carry unexpected charges. Transformers, the massive devices that step voltage up and down throughout the electrical grid, can be overloaded by currents they were never designed to handle. The cascading effects of such an event could bring our modern, electrified world to a halt. The risks associated with such solar events are not speculative. This is the assessment of engineers and physicists who specialize in space weather. The question is not whether such an event will occur, but when. And now, as we watch the largest sunspot complex of solar cycle 25 rotate across the sun's disk, we must consider the possibility that the Earth may be in the path of a major solar event, one that could disrupt the very infrastructure upon which our modern civilization relies. In March 1989, a geomagnetic storm led to the collapse of the Hydro-Quebec power grid, leaving 6 million people without electricity for 9 hours. That storm, though significant, was only about a third as strong as the Carrington event. In July 2012, a Carrington-class solar storm erupted from the Sun and crossed Earth's orbital path. By sheer luck, our planet had passed that point in its orbit 9 days earlier, narrowly missing what could have been a devastating catastrophe. The sunspot we are observing now has the potential to generate a storm of similar magnitude. This is not conjecture, this is the assessment of space weather forecasters from NOAA, ESA, and observatories worldwide. The beta-gamma-delta magnetic configuration of AR4294 indicates that the stored energy is sufficient for X-class flares. Whether that energy will be released while the sunspot faces Earth, whether any resulting coronal mass ejection CME will be directed toward our planet, or whether the impact will be glancing or direct, all these questions remain unanswered. We can only observe, we can only prepare, and we can only marvel at the timing of these events. The appearance of the sunspot complex coincided with 3I, Atlas, emerging from behind the Sun. But this is a statement of chronology, not causation. The Sun regularly produces large sunspots during periods of high solar activity, and solar cycle 25 has proven to be more active than initially predicted, with monthly sunspot numbers exceeding forecasts by significant margins. The emergence of a major sunspot complex in late 2025 is consistent with the normal behavior of our star during solar maximum. However, the Sun is an extraordinarily dynamic system of almost incomprehensible complexity. While we understand the broad principles of the solar dynamo, the specifics remain elusive. We cannot predict exactly when sunspots will appear or how large they will grow, nor can we predict with certainty which magnetic configurations will lead to major solar flares. We understand the physics, but the solar system's dynamics are too intricate for precise prediction. Could some external influence affect solar activity? At first glance, this might seem absurd. The Sun contains 99.8% of all the mass in our solar system, and its internal processes operate on scales of energy and matter that far surpass anything within human experience. The idea that a comet, even one from another star system, could influence the Sun seems almost laughable. But consider the magnetic environment. 3I. Atlas passed through regions of intense solar magnetic field during its perihelion approach. The object itself may carry magnetic properties, either from remnant magnetism or induced fields resulting from its interaction with the solar wind. At the speeds involved, any interaction between 3I, Atlas's magnetic signature, and the Sun's complex magnetic structure would have been brief but potentially significant. We have no data from the perihelion passage due to the hidden window. We do not know what happened when 3I, Atlas, was closest to the Sun, traveling at maximum velocity through the most intense magnetic environment it would ever encounter. What we do know is what occurred afterward. A sunspot complex of historic proportions emerged, precisely when the interstellar visitor reappeared from solar conjunction. The magnetic configuration of this complex has the potential to produce flares that could threaten technological civilization. The timing is so exact that it demands attention. Even if we cannot yet explain it, the Sun has wounded itself before, and it will undoubtedly do so again. The question hanging over December 2025 is whether this particular wound is a coincidence or a consequence of the events surrounding 3I, Atlas's passage. As the Sun continues to rotate, the sunspot complex drifts slowly toward the western limb, each day reducing the angle at which any flare could strike Earth. In about 2 weeks, AR 4294 will rotate out of view, passing to the far side of the Sun, where its potential effects on Earth will be temporarily blocked. However, sunspots can survive multiple rotations. The magnetic structures that generate them persist beneath the surface, even when their visible manifestations disappear. AR 4294 may return around Christmas, rotating back onto the Earth-facing disk just as 3I, Atlas, reaches its closest approach on December 19th. At a distance of 269 million kilometers, an interstellar object will be at its nearest point to Earth, potentially aligned with a historic sunspot pointed directly at our planet, one that has been approaching for 8,000 years. The physics behind sunspot evolution is complex and not fully understood. Magnetic flux emerges from the solar interior, creating the dark regions we observe on the photosphere. Over time, the flux can disperse, spreading across the solar surface and losing the concentration that defines a sunspot. Or it can persist, maintaining its coherence through multiple rotations. The factors that determine whether a sunspot will endure are not entirely predictable. Larger, more complex sunspot regions tend to last longer, and regions embedded in active zones with ongoing magnetic flux may be reinforced by new material. However, exceptions exist in both directions. AR 4294 is part of a larger active complex that has been producing sunspots for weeks. The underlying magnetic structure suggests ongoing activity in the convection zone beneath, a favorable indicator for persistence. If AR 4294 survives its rotation around the far side of the Sun and returns to face Earth, the timing could be extraordinary. On December 19th, 3I, Atlas, will make its closest approach to Earth. By December 25th, AR 4294 may return, once again facing the Earth. Just as 3I, Atlas, reaches its closest point. This synchronicity of events, the passage of an interstellar object, the return of a massive sunspot complex, and their potential alignment makes December 2025 a pivotal moment in both astronomical and technological history. The convergence of these phenomena raises profound questions that remain unanswered. What will happen if the sunspot complex erupts during this critical time? What will be the impact on Earth? And how will we respond? These questions may define not just the next 2 weeks, but the future of human civilization as we face the potential for unprecedented solar activity and its far-reaching consequences. The week between December 19th and 25th, represents the peak of this extraordinary convergence. A solar flare during this critical window would produce effects on Earth within just 8 minutes, the light travel time from the Sun to our planet. A coronal mass ejection CME would follow shortly after, reaching Earth anywhere from 15 to 36 hours, depending on its speed. The impact of this CME would coincide with the presence of the interstellar visitor at its nearest point to Earth. This coincidence, while striking, does not inherently imply a connection. The Sun has no awareness of comets passing through its system, and the interstellar object has no power to influence solar magnetic fields. At least as we understand the laws of physics, the timing of these events is what it is, remarkable, but presumptively meaningless. However, this convergence invites our attention and focuses our minds on possibilities that might otherwise remain abstract. The threat of space weather becomes tangible when a historic sunspot faces our planet, and the mystery of interstellar visitors takes on new urgency when one approaches its closest pass. While we cannot control the Sun or redirect the comet, we can only observe, prepare, and hope that the wound on the Sun heals before it bleeds again. This brings us to the Carrington event on the morning of September 1st. The English astronomer Richard Carrington was in his private observatory in Red Hill, south of London, observing the Sun as he often did. Carrington was well known for his meticulous solar observations. He had already made significant contributions to our understanding of solar rotation, including demonstrating that the Sun rotates faster at the equator than at the poles. On that particular Thursday morning, Carrington was sketching a large group of sunspots when something extraordinary occurred. A brilliant flash of white light erupted from the sunspot group, lasting only 5 minutes. But its intensity was so extraordinary that it was visible even against the blazing disk of the Sun itself. Carrington immediately recognized that he was witnessing something unprecedented. He rushed to find another observer, and by the time he returned, the flash had faded. Richard Hodgson, another English astronomer working independently, had seen the same event. Their simultaneous observations later confirmed that the flash was indeed real and not an artifact of equipment or perception. Carrington suspected a connection between this solar flare and the terrestrial effects that soon followed. But he was cautious. When the most intense geomagnetic storm in recorded history struck Earth the following day, he wrote that one swallow does not make a summer, understanding that correlation alone does not establish causation. On September 2nd, the geomagnetic storm defied easy explanation. Telegraph systems across Europe and North America failed catastrophically. Operators reported receiving electrical shocks from their equipment, and telegraph paper caught fire. Pylons threw sparks. And in one of the most remarkable details of the event, some operators discovered they could continue sending and receiving messages even after disconnecting their power supplies. The aurora itself was providing enough current to operate the equipment. The aurora was visible around the world, with gold miners in the Rocky Mountains waking up to prepare breakfast, thinking dawn had arrived early. In the northeastern United States, people reported being able to read newspapers by the light of the sky. In the Caribbean and Hawaii, areas that had never seen the northern lights, the sky glowed red and green with colors that seemed impossible. The geomagnetic storm lasted for days. When it finally subsided, the world returned to normal. Telegraph lines were repaired. The operators recovered from their shocks, and the event was relegated to scientific literature as a curiosity, a demonstration of solar power that few expected to see repeated in their lifetimes. Fast forward 166 years, and we now live in a civilization that the telegraph operators of 1859 could not have imagined. Every aspect of modern life depends on electromagnetic systems. The electricity flowing through our homes comes from generators linked by thousands of kilometers of high-voltage transmission lines. Our communications networks are connected through satellites, fiber optic cables beneath oceans, and wireless signals bouncing from tower to tower across continents. Our financial systems process transactions through data centers that consume more electricity than some small nations. Our transportation systems rely on GPS signals beamed from satellites, which would be among the first casualties of a major geomagnetic storm. In 1859, the Carrington event did not destroy civilization because it simply did not rely on technology that could be destroyed. Back then, we had telegraph lines and nothing else. The storm was a disruptive inconvenience, a wonder, and a scientific puzzle, but it was not an existential threat. Today, the equation has changed. Let me walk through what would happen if a Carrington-class geomagnetic storm struck Earth tomorrow. This is not speculation, this is the analysis of engineers, physicists, and policy experts who have studied the problem in great detail. The first warning would come from satellites positioned at the first Lagrange point, about 1.5 million kilometers sunward from Earth. The Deep Space Climate Observatory (DSCOVAVA) and similar spacecraft monitor the solar wind continuously. When a fast-moving CME approaches, these instruments detect changes in particle density and magnetic field orientation. The warning time depends on the speed of the CME, ranging from as little as 15 minutes for the fastest events to perhaps an hour for slower ones. 15 minutes is not enough time to take meaningful action. When the CME strikes Earth's magnetosphere, it would compress on the sunward side and stretch on the night side, causing magnetic field lines to reconnect and dump energy into the upper atmosphere. Currents would begin to flow, not the kind of currents we use, but geomagnetically induced currents created when the changing magnetic field interacts with long conductors on Earth's surface. Power transmission lines, for example, would act as massive antennas, picking up current from the fluctuating field. The longer the conductor, the greater the induced voltage. Transcontinental power lines, which can stretch for thousands of kilometers, would experience the largest effects. Transformers are the critical vulnerability. Electrical power is transmitted at high voltage because high voltage reduces resistive losses over long distances. At generating plants, transformers step up the voltage, and at substations near consumers, transformers step it down. These devices are massive, expensive, and difficult to manufacture. A large power transformer weighs hundreds of tons and costs millions of dollars. More importantly, they are custom built. There is no stockpile of spare transformers waiting to replace those that are damaged. Geomagnetically induced currents can destroy transformers in minutes. The DC component of the induced current saturates the transformer core, causing it to overheat. The windings can melt, and the insulating oil can catch fire. Once a transformer fails, the power it handles must be redirected, potentially overloading the next transformer in line. The 1989 Quebec blackout demonstrated this cascade on a limited scale. A geomagnetic storm, about 3 times weaker than the Carrington event, triggered a sequence of failures that brought down the entire Hydro-Quebec grid in just 90 seconds. The potential impact of a Carrington-class storm today would be far greater, affecting not only power grids but also communications, financial systems, and our daily infrastructure in ways we are not fully prepared to handle. In 1989, a geomagnetic storm caused a major power outage, leaving 5 million people in Quebec without electricity for 9 hours. The storm was significant, and transformers were damaged in New Jersey. Fluctuations rippled through the interconnected North American grid. However, a Carrington-class solar storm would be orders of magnitude worse. Studies commissioned by the US government and Lloyd's of London have attempted to estimate the damage, and the numbers are staggering. Direct damage to electrical infrastructure could exceed $600 billion in the United States alone, and the total economic impact, including cascading effects on other sectors, could reach $2.6 trillion. Power outages in some regions could last not just hours or days, but potentially months or even years. Consider what happens when the power goes out and it doesn't come back on. Hospitals have backup generators, but these generators require fuel. Without power, Fuel pumps at gas stations stop working. Without fuel, trucks cannot deliver essential supplies. Without supplies, the generators run dry. Medical equipment fails. Refrigeration fails. Food spoils. Water treatment plants shut down. And sewage systems back up. Modern cities, designed for convenience and efficiency, become vulnerable when supply chains collapse. A typical supermarket holds about 3 days' worth of food for the local population. Warehouses may have more. But without transportation to move goods from warehouse to store, the reserves remain inaccessible. Communications would fail almost immediately. Cellular networks depend on towers that require power. And internet infrastructure depends on data centers that rely on electricity for cooling. Satellite communications, 2, depend on ground stations that require power. The systems we use to coordinate emergency responses would be among the first casualties of the emergency. This is not a scenario from science fiction. This is the assessment of experts who study infrastructure resilience. The United States Federal Energy Regulatory Commission has acknowledged the risk. The United Kingdom's Royal Academy of Engineering has issued reports. The insurance industry has quantified potential losses. Everyone who examines the problem reaches the same conclusion. We are vulnerable, and we're not prepared. The sun does not care about our preparations. The probability of a Carrington-class event in any given year is low. Estimates range from 1% to 12% per decade, depending on the statistical models and historical data used. Over the course of a human lifetime, the cumulative probability becomes significant. Over the lifespan of our current electrical infrastructure, the question shifts from whether such an event will occur to when. Some preparations are possible. Utilities can install devices that detect geomagnetically induced currents and trip circuits before transformers are damaged. Grid operators can reduce loads during storm warnings, decreasing the stress on vulnerable components. Governments can stockpile critical transformer components, though the cost and logistics of this are challenging. But these preparations require time, money, and political will, and they require acknowledging a threat that seems abstract and distant until it arrives without warning. Now, in December 2025, we find ourselves watching a sunspot complex capable of producing the flares that could drive such storms. The beta-gamma-delta magnetic configuration of AR4294 indicates stored energy sufficient to cause major events. Whether that energy will be released in our direction remains unknown. The Carrington event occurred near the peak of solar cycle 10, and we are now near the peak of solar cycle 25. While the historical parallel is not exact, it is close enough to warrant serious attention. Richard Carrington watched the sun because of his curiosity. He recorded what he saw because he believed in the value of systematic observation. He could not have known that his careful notes would become the benchmark by which future solar storms would be measured. We, on the other hand, watch the sun for different reasons. We watch because our civilization depends on it. We watch because the equation has changed, and the terms now include everything we have built. We watch because, somewhere behind the blazing disk of the sun, an interstellar visitor recently made its closest approach, hidden from our eyes during the moment of maximum potential. The Carrington event was a warning written in auroras and sparks. We have had 166 years to heed it. The sunspot facing Earth today will tell us whether we have learned anything at all. But beyond the immediate threat, there are longer-term considerations that deserve our attention. The Carrington event was not unique in Earth's history. Ice core samples from Antarctica and tree ring data from around the world have revealed evidence of even larger solar events in the distant past. The Miyake event of 774 AD, for example, produced a spike in carbon-14 that suggests a solar storm roughly 20 times more powerful than the Carrington event. Similar spikes have been identified at other points in the geological record. These ancient events, though, occurred before human civilization had developed electromagnetic infrastructure. They left traces in the chemistry of polar ice and the growth rings of trees. but they caused no technological damage because there was no technology to damage. In fact, we now realize that these past events were far more catastrophic than we previously understood. The question we face today is not just how we prepare for a solar storm of the magnitude of the Carrington event, but how we understand and respond to the growing risk of even more powerful events. As our technology advances and our dependence on electromagnetic infrastructure grows, the threat posed by solar storms becomes more than just a curiosity or a scientific anomaly. It becomes a real, existential challenge to the very systems that sustain modern life. The need to prepare for such events is no longer a matter of when, but how. The clock is ticking, and the window of opportunity to mitigate the risks posed by space weather is rapidly closing. The sun's behavior, over the course of historical timescales, has remained relatively constant. The frequency of major solar events has not significantly increased over billions of years. What has changed, however, is our vulnerability. Each new satellite launched, every new power line installed, and every new data center constructed contributes to the infrastructure that would be impacted by a major geomagnetic storm. This trend is accelerating. The space economy is expanding. The electrification of transportation is progressing, and the digitalization of finance and commerce continues to expand. Each step toward a more connected and electronic civilization increases our exposure to space weather. Yet, investment in space, weather monitoring, and infrastructure protection remains modest. The warnings are clear, the probabilities well understood, and the potential consequences have been extensively documented. Still, preparations lag far behind the growing need. Perhaps this is human nature. We are not adept at responding to rare, unpredictable, and impersonal threats. The sun gives us no advance notice of its intentions. A storm will arrive when it arrives, whether we are ready or not. And so, we watch and wait in December 2025, observing as the Sunspot complex rotates and the interstellar visitor approaches. The convergence unfolds according to the laws of physics. Laws we understand but cannot control. Whatever happens next, the Carrington equation remains unchanged. Vulnerability multiplied by impact multiplied by probability equals risk. The first two factors have been growing steadily for over a century. The third factor is for the sun to decide. Now, let's turn our attention to the 9 anomalies associated with 3I, Atlas, and the one question that arises from them. Science advances by measuring differences. When an observation aligns with our predictions, we note it and move on. When an observation deviates from expectations, we pay attention. The larger the deviation, the more attention it demands. And when multiple deviations converge around a single object, that attention intensifies. Since its discovery in July 3I, Atlas has accumulated 9 documented anomalies. Each one, when considered in isolation, can be explained by natural processes. Comets are diverse objects, and interstellar visitors come from environments we cannot directly study. The unexpected is not the same as the inexplicable, but 9 anomalies are a lot of anomalies. Let's walk through these anomalies systematically. As understanding what makes 3I, Atlas, unusual is essential to understanding why the questions persist. The first anomaly is its trajectory alignment. When an object enters our solar system from interstellar space, it can arrive from any direction. The galaxy surrounds us in 3 dimensions, so interstellar objects should be distributed more or less randomly across the celestial sphere. However, 3I, Atlas, entered our solar system at an angle within 5 degrees of the ecliptic plane. The ecliptic is the flat disk containing the orbits of the planets, defined by Earth's orbit around the Sun. For a random interstellar object to align so closely with this plane is statistically unusual. The probability of such an alignment is approximately 0.2%, or 1 in 500. While this isn't impossible or particularly rare by astronomical standards, It is the first deviation from expectation. The second anomaly is the timing of planetary approaches. The trajectory of 3I, Atlas, brought it within tens of millions of kilometers of Mars in October. Will bring it close to Venus, and will take it past Jupiter in early 2026. These close approaches to multiple planets, combined with the ecliptic alignment, create a path that seems almost designed to survey the solar system. R.V. Loeb calculated the combined probability of this trajectory occurring by chance at approximately 0.5% or 1 in 20. Ling ling ling. While this calculation has been criticized by some astronomers for potentially overestimating the unlikelihood of the trajectory, even critics acknowledge that the path of 3I, Atlas, is highly unusual. The third anomaly is the solar conjunction at perihelion. As we've discussed, 3I, Atlas, reached its closest approach to the Sun while positioned on the far side of our star relative to Earth. This geometry prevented direct observation during the most dynamic phase of the object's journey. The hidden window lasted for about 2 weeks, coinciding precisely with the moment of maximum gravitational influence and maximum solar heating. While a natural object's trajectory is determined by orbital mechanics and the position of Earth at the time, if someone were designing a trajectory to minimize observation during a critical maneuver, this is exactly what it would look like. The fourth anomaly is the anti-tail. Comets typically display tails that point away from the Sun, pushed by solar radiation and the solar wind. The dust tail gently curves along the comet's orbital path, while the ion tail points directly away from the Sun, a straight line of glowing gas. However, 3I, Atlas has displayed what observers call an anti-tail, an unusual structure that points toward the Sun rather than away from it. Anti-tails can occur naturally when Earth passes through the orbital plane of a comet and we view the dust tail from a different angle. This geometry can create an optical illusion of forward-pointing material. However, some astronomers have argued that the anti-tail of 3I, Atlas, is not adequately explained by viewing geometry alone. R.V. Loeb suggested that it might represent material being ejected forward, perhaps as a protective buffer against debris in the asteroid belt, though this interpretation remains controversial. The fifth anomaly is the mass. By analyzing the outgassing rate and gravitational influence on the object's trajectory, researchers have estimated the mass of 3I, Atlas. The results suggest a mass exceeding 33 billion tons, far larger than typical comets, and about 1 million times the estimated mass of Oumuamua. The mass of an object affects how it responds to external forces. A more massive object is less affected by outgassing, solar radiation pressure, or the buffeting of the solar wind. If 3I, Atlas, is as massive as these estimates suggest, its trajectory would be more stable than that of a typical comet, more predictable and controlled. The sixth anomaly is the chemical composition. Spectroscopic analysis of the gas surrounding 3I, Atlas, has revealed an unusual ratio of nickel to iron. In most comets, these metals are present in roughly solar proportions, reflecting the composition of the primordial material from which our solar system formed. In dry Atlas, however, nickel dominates. This nickel-rich composition is more commonly associated with industrial alloys than with natural ices. While this finding has prompted speculation about artificial origins, natural explanations remain possible. Perhaps 3I, Atlas, formed in an environment with different elemental abundances than our solar system. The seventh anomaly is the water content. Comets are often described as dirty snowballs, composed primarily of water ice mixed with dust and rock. The water content of a typical comet is substantial, driving the characteristic activity that forms the coma and tail. Yet 3I, Atlas, contains only about 4% water by mass, much lower than most comets. This suggests either a different formation environment or a history that removed most of the water. An object that spent billions of years in the cold of interstellar space would typically be expected to retain its volatile ices, not lose them. The eighth anomaly is the polarization. Light reflected from cometary dust becomes polarized, with the electric field oscillating preferentially in certain directions. The degree and type of polarization provide information about the size and composition of dust particles. 3I. Atlas has shown extreme negative polarization, unprecedented among all known comets, including the interstellar comet Oumuamua. The polarization signature suggests dust properties unlike anything previously observed in cometary environments. The ninth anomaly emerged at perihelion as 3I Atlas approached its closest point to the Sun. Space-based observatories detected a color shift. The object appeared bluer than the Sun itself, an unexpected and puzzling result. Dust scatters sunlight in a way that typically makes objects appear redder. Is not bluer. The blue color suggests either an unusual emission source or a power source hotter than the solar photosphere. This anomaly challenges our understanding of the object's composition and behavior. Taken together, these 9 anomalies present a puzzle, one that warrants attention and careful study. While each anomaly can be explained by natural causes, the accumulation of so many unusual features around a single object raises questions that cannot be easily dismissed. The story of 3I Atlas is far from over, and as we continue to observe its trajectory and the events unfolding in our solar system, the mysteries surrounding this interstellar visitor remain at the forefront of astronomical inquiry. Neither of the explanations, natural or artificial, comfortably fits the standard cometary models. 9 anomalies, 9 deviations from expectation, 9 data points that don't quite fit the template of a natural comet. Avi Loeb has proposed a rating scale for interstellar objects, ranging from 0 to 10. A score of 0 represents an object that is definitely natural, while a score of 10 represents an object that is definitely artificial. Based on the accumulated evidence, he currently rates 3I Atlas closer to the higher end of the scale, somewhere around a 4. Critics, however, point out that each anomaly has a potential natural explanation. The trajectory alignment could be a coincidence. The chemical composition might reflect formation conditions in another star system. The blue color could result from unusual gas emissions. Extraordinary claims require extraordinary evidence, and the evidence for an artificial origin remains circumstantial at best. This criticism is valid. The scientific method demands skepticism of unusual claims, especially those that might overturn our understanding of our place in the universe. The default assumption should be that 3I Atlas is a natural object, until and unless the evidence forces a different conclusion. But the critics have not made the anomalies disappear. They've offered alternative explanations, but not definitive rebuttals. The data remains ambiguous, and the question lingers: what are the odds? 9 anomalies, each individually explainable, cluster around a single object. This object arrives at the peak of solar maximum, when the Sun is most active and dangerous. Its closest approach to the Sun occurs during a 2-week window of invisibility from Earth, and a massive sunspot complex appears as the object emerges from behind the Sun. Additionally, the closest approach of the object coincides with the potential return of that sunspot to the Earth-facing disk. Each piece of the puzzle can be explained separately. The trajectory is unusual but possible. The composition is strange but not impossible. The timing is suspicious but could be coincidental. And the sunspot is natural and expected during solar maximum. But what are the odds of all these factors aligning at the same time? This is not a question science can easily answer. Statistics deals with well-defined probability spaces and events whose likelihood can be calculated from known distributions. The arrival of an interstellar object is not one of these events. We have only 3 data points in the entire history of human observation. We cannot calculate the probability of such unusual trajectories because we don't know the underlying distribution. What we can do is notice patterns. We can observe that multiple unusual features cluster around a single moment in time. We can acknowledge that the timing is striking even if we can't prove it's meaningful. The 9 anomalies of 3I, Atlas, may be nothing more than cosmic coincidence, a natural object from an unusual environment following an unusual path through our solar system. This is the most likely explanation, and it's where the evidence currently points. But the question persists, hanging in the space between the data points, in the gap between observation and explanation. And that question refuses to go away. What if we're looking at this all wrong? This brings us to the concept of the Oberth maneuver, a principle that may offer insight into 3I, Atlas's behavior. In 1929, Romanian physicist Hermann Oberth published a book called Ways to Spaceflight, which would change the way humanity thinks about traveling through space. Among its pages, buried in the text, was a counterintuitive principle that would eventually guide every interplanetary mission humanity has ever launched. The principle is simple to state, but difficult to grasp. A rocket engine is more efficient when the vehicle is moving fast than when it is moving slow. The same amount of fuel produces more change in velocity at high speeds than at low speeds. This seems wrong at first. Fuel is fuel, and thrust is thrust. How can the same engine behave differently depending on how fast it is already traveling? The answer lies in the relationship between kinetic energy and velocity. Kinetic energy increases with the square of velocity if you double your speed. You quadruple your kinetic energy. This non-linear relationship means that adding velocity to an already fast-moving object increases its energy more than adding the same velocity to a slow-moving object. A rocket engine produces thrust by expelling mass at high speed, and the energy delivered to the spacecraft depends on the reference frame. When the spacecraft is moving fast, the exhaust is left behind, with less total energy relative to the destination. More of the chemical energy from the fuel ends up as kinetic energy of the spacecraft. This is the Oberth effect. In practical terms, the Oberth effect means that the best time to fire your engines is when you're moving fastest. And when do you move fastest? At the bottom of a gravitational well. The closer you fall toward a massive body, the faster you go. The faster you go, the more efficient your burn. Every gravity assist maneuver exploits this principle. For instance, when Voyager swung past Jupiter, it used the planet's gravity to accelerate toward the outer solar system. Similarly, the Parker Solar Probe dives close to the Sun to use the Sun's gravity to reshape its orbit. The gravitational field provides free energy, and the Oberth effect maximizes the benefit. Now, let's apply this principle to 3I, Atlas, at perihelion. On October 29th, the interstellar object reached its closest approach to the Sun at a distance of approximately 203 million kilometers. At that moment, it was traveling faster than at any other point in its journey through our solar system. Its velocity exceeded 150,000 miles per hour, and the gravitational acceleration from the Sun was at its maximum. The conditions for an Oberth maneuver were optimal. If 3I, Atlas, is a natural comet, this moment would simply represent the low point of its hyperbolic orbit, where it experienced maximum speed and the greatest opportunity for gravitational assistance. However, the circumstances surrounding 3I, Atlas, raise the question: could this interstellar object have been using these gravitational forces in a way that we do not yet fully understand? Could the anomalies observed in its trajectory, its behavior, and its interactions with the solar environment suggest something more than a natural comet? The question remains open, and the mysteries surrounding this interstellar visitor continue to intrigue and challenge our understanding of the cosmos. The object swung around the Sun, gaining no net energy from the gravitational interaction, and continued on its outward trajectory. Physics, indifferent to any observer, simply played out. But if 3I, Atlas, is something else, perihelion was an opportunity. The energy available at perihelion was immense. Solar radiation at that distance delivers approximately 770 watts per square meter to any surface facing the Sun. For an object with a diameter of several kilometers, The total power received would be measured in gigawatts, comparable to the output of major nuclear power plants, delivered for free by our star. What could be done with that power? If the object carried any form of energy storage, it could have captured solar radiation during the perihelion passage, photovoltaic cells, thermal collectors, or more exotic energy harvesting systems could have harnessed a portion of the incoming flux. The stored energy could then be used for propulsion, for powering onboard systems, or for purposes we cannot yet anticipate. If the object carried any form of propulsion, perihelion was the optimal moment to utilize it. A small velocity change at perihelion translates into a much larger change in the final trajectory than the same velocity change applied elsewhere. The Oberth effect magnifies the impact of any propulsive burn. If the object carried any payload intended for deployment, perihelion offered advantages beyond mere efficiency. The intense solar heating would have provided thermal energy for processes requiring heat. The gravitational forces would have been at their maximum, which could have been useful for separation dynamics. And the solar conjunction meant that any deployment would have been hidden from Earth-based observation. This last point deserves emphasis for about 2 weeks around perihelion. 3I. Atlas was unobservable from Earth. Telescopes could not penetrate the solar glare. Our best instruments were blind. During this window, anything could have happened and we would not have seen it. What might we have missed? Loeb has suggested the possibility of a mothership scenario. In this hypothesis, the main body of 3I, Atlas, would continue on its original trajectory, visible and trackable. But smaller objects released during the perihelion passage could follow different paths. These hypothetical mini-probes could use the gravitational slingshot effect to redirect toward other destinations toward Mars, Venus, or Earth. The physics is not speculative. We use exactly these techniques in our own space missions. The mathematics of gravitational assists has been understood for decades. If an advanced civilization wished to seed our solar system with observational platforms, perihelion passage would be an excellent opportunity to do so. But would we have seen the separation? This is where the hidden window becomes significant. Tidal forces from the Sun at perihelion could have provided natural-looking cover for any deployment. Comets sometimes fragment under solar heating, with pieces breaking away from the main nucleus and following slightly different trajectories. If 3I, Atlas, fragmented during perihelion, these fragments might initially appear as natural pieces. However, over time, any propulsive adjustments would cause the fragments to diverge from purely gravitational paths. The tidal forces of the Sun would separate objects on natural trajectories from objects on powered trajectories. By December, any significantly different paths should become detectable through careful observation. This is exactly what astronomers are watching for. The International Observation Campaign that resumed in November is not simply tracking the main body of 3I, Atlas. It is searching for any associated objects, any fragments, any unexplained companions. The Hubble Space Telescope, the James Webb Space Telescope, and ground-based observatories around the world are all contributing to a systematic survey of the region around the interstellar visitor. So far, no confirmed detections of secondary objects have been announced. The main nucleus appears intact, and its trajectory remains consistent with purely gravitational motion, with no evidence of propulsive maneuvers. But the observation campaign is ongoing. The data is still being collected, and the question of what happened during the hidden window remains open. Let me be clear about what we are not claiming. We are not asserting that 3I, Atlas, performed an Oberth maneuver. We are not claiming that it released probes toward Earth or any other destination. We are not announcing the discovery of artificial objects in our solar system. What we are doing is acknowledging a gap in our knowledge. The perihelion passage occurred during a period when observation was impossible. The physics of the situation would have favored any propulsive action. The object would have maximized the efficiency of any velocity change, and the solar conjunction would have hidden any deployment from terrestrial detection. If 3I, Atlas, is a natural comet, This gap in observation is merely an inconvenience. The object swung around the sun and continued on its way. We missed the most dramatic part of the show. But nothing unusual happened. But if 3I, Atlas, is something else, the gap is a window of opportunity. The hidden window was not just a limitation of our observation, it was a moment when an artificial object could have acted without being watched. We do not know which interpretation is correct. The evidence currently favors the natural explanation. A comet, even an unusual one, is more likely than an alien spacecraft. Occam's razor suggests we should prefer the simpler hypothesis until the evidence demands otherwise. But the hidden window prevents us from closing the question definitively. We cannot prove that nothing happened at perihelion. We can only observe what came after and look for anomalies that would suggest something did happen. The sunspot that appeared as 3I, Atlas, emerged from behind the sun may be one such anomaly. Or it may be coincidence. We do not know. The trajectory of 3I, Atlas, in the coming weeks will provide another data point. If the object continues on a purely gravitational path, that supports the natural interpretation. But if any deviation is detected, any unexplained acceleration or deceleration that would require further explanation, we are watching, waiting, and gathering data, fully aware that whatever we discover next could change our understanding of the cosmos, whether we are looking at a natural phenomenon or something else. The question of 3I, Atlas, is far from settled. The mystery continues to unfold. The presence or absence of secondary objects will be highly informative. If fragments appear that were not expected from natural cometary processes, that would be significant. If no unusual companions are detected, it would support the conclusion that the perihelion passage was uneventful. We are watching, measuring, and waiting. The Oberth maneuver is a proven technique, one that we use in our own spacecraft. The physics are well understood, and the only question is whether an interstellar visitor made use of it too. Perihelion has passed, and the hidden window has closed. But the implications of those 2 weeks will echo through December and beyond as 3I, Atlas, continues its journey toward its closest approach to Earth. What happened at perihelion we may never know for certain. But the question itself is worth asking, because the answer, whatever it may be, matters. The physics of stellar flybys have been studied extensively, though primarily in the context of our own spacecraft rather than incoming visitors. Every deep space mission uses gravity assists to shape its trajectory. The Voyager probes used Jupiter's gravity to accelerate toward the outer planets. Cassini used Venus, Earth, and Jupiter before reaching Saturn. New Horizons used Jupiter to shorten its travel time to Pluto. The mathematics is well understood. A spacecraft approaching a massive body gains velocity as it falls into the gravitational well. If it passes behind the body relative to the body's motion through space, it steals some of the body's orbital momentum, accelerating in the process. If it passes in front, it gives momentum back and decelerates. For 3I, Atlas, the Sun provided the gravitational well. The object's trajectory carried it around the back of the Sun relative to the Sun's motion through the galaxy. This geometry would have provided a small boost to the object's velocity. Although this effect is negligible for an object already traveling at interstellar speeds, the Oberth effect operates independently of simple gravity assists. The efficiency gained from burning propellant at high velocity applies regardless of the geometry. At perihelion, 3I, Atlas was moving at its maximum velocity. Any propulsive action at that moment would have been maximally efficient. Consider what could be accomplished with even modest propulsion at perihelion. A velocity change of just 1 meter per second, hardly more than a walking pace, would alter the trajectory enough to be detectable over the following months. Astronomers are watching for exactly such deviations. The non-gravitational acceleration observed in Oumuamua was on this order of magnitude, approximately 1 millimeter per square second at perihelion. For Oumuamua, the cause of this acceleration remains disputed. Outgassing of invisible volatiles is the leading natural explanation, but the mechanism has not been definitively established. If 3I, Atlas, shows a similar anomalous acceleration, the same debate will likely recur. A larger velocity change could redirect the trajectory entirely. At interstellar speeds, even small angle changes translate into vast differences over time. An object passing through our solar system on one trajectory could, with sufficient propulsion at perihelion, depart on a completely different heading. We would eventually detect such a change. The orbital mechanics are precise. Any deviation from the predicted path would be noticeable as the object moves against the background stars. But by the time we detect it, the maneuver would already be complete. Whatever purpose it served would have been accomplished. The hidden window meant that any such maneuver occurred without witnesses. This may be coincidence. It may be the inevitable result of orbital geometry and our planet's position, or it may be something else. The question is not whether the Oberth effect is real, it is. We use it constantly in our space program. The question is whether an interstellar visitor made use of it during the 2 weeks when no telescope on Earth could watch. In 1950, physicist Enrico Fermi was having lunch at Los Alamos National Laboratory when the conversation turned to the question of extraterrestrial life. After some discussion of the probability of other civilizations existing in our galaxy, Fermi famously asked, "Where is everybody?" This became known as the Fermi paradox. The galaxy is old, approximately 13 billion years. It contains hundreds of billions of stars, many of which have planets in habitable zones. Even if intelligent life is rare, and even if it emerges on only a tiny fraction of suitable worlds, the sheer numbers suggest that civilization should be common. Yet, we see no evidence of anyone else. No signals, no artifacts, no visitors. Many explanations have been proposed. Perhaps life is rarer than we think. Perhaps intelligence is a cosmic accident, unlikely to repeat. Perhaps civilizations inevitably destroy themselves before becoming spacefaring. Perhaps the distances between stars are simply too vast to bridge. But there is another explanation, darker than the rest. In 2008, Chinese author Liu Cixin published a novel called The Dark Forest, which proposed a solution to the Fermi paradox that has since become one of the most discussed ideas in the literature of extraterrestrial intelligence. Liu suggested that the universe is like a dark forest. Every civilization is a hunter stalking through the trees, moving silently, trying not to be noticed. Any civilization that reveals itself becomes a target. Any civilization that detects another faces a terrible choice. The stakes are existential. The logic proceeds from simple premises: all life seeks survival. This is definitional. A species that did not prioritize its own continued existence would not last long enough to become a civilization. Resources are limited. Planets can be destroyed. Even in a vast universe, the materials and energy needed for survival are finite. Competition is inevitable. Communication is slow. Interstellar distances are measured in light years. A message sent to another civilization might not receive a reply for decades or centuries. In that time, circumstances could change dramatically. The civilization you contacted as friends might become enemies. The technology you shared could be turned against you. Trust becomes impossible. You cannot verify the intentions of a civilization light years away. They cannot verify yours. Even if both parties genuinely desire peace, neither can be certain the other does. The uncertainty is fundamental and cannot be resolved. Given these premises, what is the rational course of action when you detect another civilization? The dark forest hypothesis answers brutally: you strike first. If you reveal yourself, you become a target. If you wait to assess the other civilization's intentions, they might develop weapons capable of destroying you before you can respond. If you attempt to communicate, you reveal your location and technological level, providing valuable intelligence to a potential enemy. The only safe course is preemptive destruction. This logic creates a universe of terrified silence. Every civilization that survives does so by hiding. Every civilization that makes itself known is destroyed. The galaxy appears empty not because we are alone, but because every civilization that understands the rules hides from the others. It is a bleak vision, but it may also be wrong. Critics have pointed out numerous problems with the dark forest hypothesis. It assumes a particular kind of risk aversion that may not be universal. It ignores the potential benefits of cooperation. It treats all civilizations as rational actors following the same logic, which seems unlikely given the diversity of life on Earth alone. The question of what 3I Atlas is, and whether it has made use of techniques like the Oberth maneuver, adds another layer of complexity to the discussion of extraterrestrial intelligence and the vast unknowns of the universe. Whether we are looking at a natural object or something else, the possibilities are as unsettling as they are intriguing. But the dark forest hypothesis does not need to be correct for it to be relevant. It only needs to be possible. If even one civilization in the galaxy operates according to dark forest logic, the consequences could be severe. A single species with the technological capability and the willingness to destroy potential rivals could reshape the galactic landscape. Everyone else would either hide, be destroyed, or adopt the same strategy. And this brings us back to 3I Atlas. If the dark forest hypothesis describes reality, what would a reconnaissance probe look like? It would not announce itself. It would not transmit signals. It would not display obvious signs of artificial origin. It would move through target systems quietly, gathering information and avoiding detection. It might disguise itself as a natural object. Comets are common in the universe. Every star system likely has its own population of icy bodies, remnants from planetary formations scattered into the void by gravitational interactions. An interstellar comet would not be surprising. It would be expected. It would be the perfect camouflage for something else. A probe designed to look like a comet would have a nucleus of rock and ice. It would outgas as it approached a star, developing a coma and tail. It would follow a trajectory consistent with gravitational physics. It would do comet-like things, but it might also do other things hidden beneath its cometary appearance. It might carry instruments for observing planetary systems, such as cameras, spectrometers, radio receivers, or sensors of types we cannot anticipate. The outgassing that makes it look like a comet could also obscure the heat signatures of active systems. It might carry payloads for deployment, small observers sent toward planets of interest, relays for transmitting collected data back to its origin, or something more direct. It could even be designed to interact with the target star. This is where the sunspot becomes relevant again. In the context of the dark forest, a civilization that wishes to neutralize a potential rival without revealing itself would prefer indirect methods. A direct attack reveals your existence and location, but if you could trigger a natural-seeming catastrophe, the cause might never be traced back to you. A solar event would be the perfect weapon. A sufficiently powerful coronal mass ejection CME could strip away a planet's atmosphere. It could sterilize the surface with radiation. Even a less extreme event, like a solar storm comparable to the Carrington event, could collapse the technological infrastructure of a civilization at Earth's level of development. Power grids destroyed, communications disrupted. The cascading effects could take years to recover from, and it would all look natural. The sun produces storms. Sunspots appear and vanish. No external cause would be suspected. Is it possible to trigger such an event artificially? We don't know. Our understanding of solar physics is incomplete. We know that magnetic reconnection releases energy, but we cannot predict exactly when reconnection will occur or how powerful it will be. The sun is a chaotic system, sensitive to initial conditions that are difficult to model, but our ignorance does not guarantee impossibility. A civilization millions or billions of years more advanced than ours might understand the sun better than we understand our own electrical circuits. They might have developed techniques for influencing stellar activity that we cannot yet imagine. Or they might simply wait. An object passing through a solar system could observe and report. The parent civilization could use that intelligence to predict when natural solar activity would provide an opportunity. No manipulation would be required. only patience and timing. I am speculating now. I want to be clear about that. There is no evidence that 3I, Atlas, is a weapon. There is no evidence that it caused the sunspot, AR4294. There is no evidence that any civilization operates according to dark forest logic. What there is, however, is a framework for thinking about risk. The dark forest hypothesis suggests that the absence of evidence is not evidence of safety. It suggests that an advanced civilization might go to great lengths to avoid detection. It suggests that apparently natural phenomena might not be natural at all. These suggestions are disturbing. They're also unfalsifiable, which makes them poor science. You cannot prove that the universe is not a dark forest. The absence of hostile civilizations attacking us could mean they do not exist, or it could mean they have not found us yet, or it could mean they are acting through means we do not recognize. But the convergence of events in December 2025 invites consideration of scenarios we would normally dismiss. An interstellar object with 9 documented anomalies. A hidden window at perihelion when anything could have happened. A historic sunspot appearing as the object emerged from behind the sun. A trajectory bringing the visitor to its closest Earth approach, just as the sunspot might return for another rotation. Each piece has a natural explanation, but the pattern, when viewed through the lens of the dark forest, looks like something else. It looks like careful positioning. It looks like plausible deniability. Perhaps it is all coincidence. Perhaps we are reading too much into these anomalies, but the sheer number of them and the timing of the events continues to raise unsettling questions. Is it possible that the universe is truly a dark forest? With civilizations hiding from each other in fear of destruction, could the arrival of 3I, Atlas, be more than just an astronomical curiosity? The answer remains unknown. But the search for understanding will undoubtedly continue. As we observe, analyze, and question, we may one day uncover the deeper meaning behind this extraordinary visitor. Until then, the question will remain, what are we truly looking at? The dark forest hypothesis does not need to be proven for it to be relevant. It only needs to be possible. If even one civilization in the galaxy operates according to dark forest logic, the consequences could be catastrophic. A single species with the technological capability and willingness to destroy potential rivals could reshape the galactic landscape, forcing everyone else to hide, be destroyed, or adopt the same strategy. This brings us back to 3I, Atlas. If the dark forest hypothesis is valid, what would a reconnaissance probe look like? It would not announce itself. It would not transmit signals. It would not display obvious signs of artificial origin. It would move through target systems quietly, gathering information without revealing its presence. It could disguise itself as a natural object. Comets are common in the universe. Every star system should have its own population of icy bodies, remnants of planetary formation scattered into the void by gravitational interactions. An interstellar comet would not be surprising. In fact, it would be expected. It would be the perfect camouflage for something else. A probe designed to look like a comet could have a nucleus of rock and ice. As it approached a star, it would outgas, developing a coma and tail. It would follow a trajectory consistent with gravitational physics. It would behave like a comet, but it might also do other things hidden beneath the surface. It could carry instruments for observing planetary systems, cameras, spectrometers, radio receivers, sensors of types we can't yet anticipate. The outgassing that makes it appear comet-like could also obscure the heat signatures of active systems. It might carry payloads for deployment, small observers sent toward planets of interest, relays for transmitting collected data back to its origin, or something more direct. It might even be designed to interact with the target star itself. This is where the sunspot becomes relevant again. In the dark forest, a civilization wishing to neutralize a potential rival without revealing itself would prefer indirect methods. A direct attack reveals your existence and location. But if you could trigger a natural-seeming catastrophe, the cause might never be traced to you. A solar event would be the perfect weapon. A sufficiently powerful coronal mass ejection CME could strip away a planet's atmosphere. It could sterilize the surface with radiation. Even a less extreme event, like the Carrington storm, could collapse the technological infrastructure of a civilization at Earth's level of development. Power grids destroyed. Communications disrupted. Cascading effects could take years to recover from. And it would all seem completely natural. The sun produces storms. Sunspots appear and vanish. No external cause would be suspected. Is it possible to trigger such an event artificially? We don't know. Our understanding of solar physics is incomplete. We know that magnetic reconnection releases energy, but we cannot predict exactly when this will happen or how powerful the release will be. The sun is a chaotic system, sensitive to initial conditions that are difficult to model, but our ignorance does not guarantee impossibility. A civilization millions or billions of years more advanced than ours might understand the sun better than we understand our own electrical circuits. They might have developed techniques for influencing stellar activity that we cannot yet imagine. Or they could simply wait, using the natural behavior of the sun to predict when an event would be most likely to occur. Without any manipulation required, just patience and timing. I am speculating here. I want to be clear about that. There is no evidence that 3I, Atlas, is a weapon. There is no evidence that it caused the sunspot, AR4294. There is no evidence that any civilization operates according to dark forest logic. What I am doing is acknowledging a gap in our knowledge. The perihelion passage occurred during a period when observation was impossible. The physics of the situation would have favored any propulsive action. The object would have maximized the efficiency of any velocity change, and the solar conjunction would have hidden any deployment from terrestrial detection. If TRES-I, Atlas, is a natural comet, this gap in observation is merely an inconvenience. We missed the most dramatic part of the show. But nothing unusual happened. However, if 3I, Atlas, is something else, this gap is a window of opportunity. The hidden window was not just a limitation of our observation. It was a moment when an artificial object could have acted without being watched. We don't know which interpretation is correct. The evidence currently favors the natural explanation. A comet, even an unusual one, is more likely than an alien spacecraft. Occam's razor suggests we should prefer the simpler hypothesis until the evidence demands otherwise. But the hidden window prevents us from closing the question definitively. We cannot prove that nothing happened at perihelion. We can only observe what came after and look for anomalies that might suggest something did happen. The sunspot that appeared as 3I, Atlas, emerged from behind the sun may be one such anomaly. Or it may be coincidence. We do not know. The trajectory of 3I, Atlas, in the coming weeks will provide another data point. If the object continues on a purely gravitational path, that would support the natural explanation. But if any deviation is detected, any unexplained acceleration or deceleration, it would require further investigation. As of early December 2025, the sunspot complex AR4294 through AR4298 remains active, but has not yet produced a Carrington-class event. Multiple M-class flares have erupted, and several class events have been recorded. On December 8th, the adjacent region, AR4299, announced its return with an X1, Noor Flare, causing radio blackouts over portions of the daylight Earth. However, the major event, the one capable of reshaping our technological infrastructure, has not yet occurred. The beta-gamma-delta magnetic configuration stores enormous energy, and the potential remains for a large flare. The release has not come. This is not unusual. Sunspots often build in complexity without producing major flares. The energy can dissipate gradually through smaller events. Or the magnetic configuration can simplify as field lines reconnect in minor cascades. Not every loaded gun fires, but the gun remains loaded. Meanwhile, 3I, Atlas continues its journey outward from the sun. Having emerged from the hidden window of solar conjunction in early November, the object is now visible to Earth-based observers during evening twilight. The coma, the fuzzy envelope of gas and dust surrounding the nucleus, has grown brighter as expected following the intense heating at perihelion. The trajectory remains consistent with gravitational physics, and no propulsive maneuvers have been detected. No secondary objects have been confirmed. The main body appears intact, with a nucleus estimated between 400 meters and 6 kilometers in diameter. Depending on assumptions about reflectivity and density, December 19th approaches. On that date, 3I Atlas will reach its closest point to Earth. At a distance of approximately 269 million kilometers, about 1.8 times the distance from Earth to the Sun. In human terms, this is not close, and you won't be able to see it with the naked eye. It won't fill the sky like a second moon. However, in terms of interstellar objects, this is an intimate encounter. We've never had such a close approach by a confirmed visitor from beyond our solar system. Oumuamua was detected only after it had already passed its closest point and was speeding away. Borisov never came particularly close to Earth. But 3I Atlas offers an unprecedented opportunity for study. The observation campaign is in full swing. The Hubble Space Telescope has been allocated time for imaging. The James Webb Space Telescope is gathering infrared data that could reveal details about the nucleus composition. Ground-based observatories around the world are tracking the object's position with exquisite precision, refining its trajectory to detect any deviation from gravitational predictions. The European Space Agency's JUICE mission, currently en route to Jupiter, passed within 64 million kilometers of 3I Atlas in early November. Its cameras captured images that are still being analyzed. With data expected to be released in early 2026, NASA's Juno spacecraft, orbiting Jupiter, will also have an opportunity to observe the object when it makes its closest approach to that planet in March 2026. As we continue to observe, we are left with many questions. We watch, measure, and wait. And as the events of December 2025 unfold, we are reminded that sometimes the universe holds its secrets close, waiting for the right moment to reveal them. The convergence of these celestial events may be the beginning of a new chapter in our understanding, or perhaps a chapter we may never fully comprehend. The questions remain, and the search for answers continues. By the time 3I Atlas moves well on its way out of the solar system, any remaining activity should still be detectable. We are gathering data, carefully watching, and learning what we can while the opportunity remains. But the two events, the Sunspot and 3I Atlas, continue to converge. The Sunspot complex, AR4294, is slowly rotating toward the western limb of the Sun. In about 2 weeks from today, it will pass out of view, carried by the Sun's rotation to the far side, where its flares cannot directly affect Earth. This provides a window of relative safety. Any flares that occur while the sunspot faces away from us will release their energy into empty space, not toward our planet. However, sunspots can survive multiple rotations. The magnetic structures creating sunspots persist beneath the solar surface, even when the visible manifestations disappear. If AR4294 remains coherent during its passage across the far side, it could return to the Earth-facing disk around late December. The timing would coincide with the days following 3I Atlas's closest approach. The probability of this return is uncertain. Sunspots decay, and magnetic configurations simplify. Some large regions dissipate entirely during a single solar rotation. Others persist for months, circling the Sun repeatedly, producing flares every time they face Earth. The forecasters at NOAA's Space Weather Prediction Center are closely monitoring the situation, with their assessments updated daily, incorporating the latest observations of magnetic field strength and complexity. As of this recording, the outlook remains elevated but not extreme. G1 to G2, geomagnetic storm conditions are possible due to ongoing activity, but the chance of a major event remains low. However, is not zero. Think about that for a moment. We have a sunspot complex that's 90% the size of the one that caused the Carrington event. It carries the most dangerous magnetic classification our systems can assign. It is currently facing Earth and will return to face us again in approximately 4 weeks. And in the intervening period, an interstellar object with 9 documented anomalies will reach its closest approach to Earth. The timing creates a window from December 19th, when 3I, Atlas, reaches its closest approach, through approximately December 25th, when AR 4294 could rotate back into view. Earth finds itself at the intersection of 2 unusual events. One is certainly natural, the other is almost certainly natural, but together they create a convergence that feels significant, even if we cannot prove it is meaningful. Let me be careful here, nothing has happened yet. The sunspot has not produced a Carrington-class flare. The interstellar object has not deviated from its expected trajectory. All observations are consistent with natural phenomena following natural laws. But we are in the quiet before. History is full of moments that seemed calm until they weren't. The hours before major earthquakes often feel ordinary. The days before financial crises often seem stable. The months before pandemics often proceed as normal. We are poor at recognizing the build-up to events that have not yet occurred. The infrastructure that protects us from space weather is better than it was in 1859, but it remains inadequate. Satellites can be placed in safe mode during solar storms, reducing their vulnerability. Power grid operators can take protective measures if given a warning. But the warning time for a fast-moving coronal mass ejection CME can be as little as 15 minutes. That is not enough time to implement comprehensive protections. If a Carrington-class event occurred tomorrow, we would face consequences ranging from severe to catastrophic. Studies have been done. Estimates have been published. yuan, 6 trillion in economic damage. Power outages lasting months. Cascading failures in communications, transportation, finance, and healthcare. The recovery would take years. This is not fear-mongering. This is the assessment of experts who have studied the problem. The threat is real, whether or not it materializes this month, this year, or this decade. And now we wait. 3I, Atlas, is approaching. The sunspot complex continues to rotate. The space weather forecasters continue to monitor. The observation campaigns continue to gather data. The world continues to function, dependent on electromagnetic systems that could fail without warning. The quiet before is not peace. It is suspense. Something may happen in the coming weeks. A flare of historic proportions. An anomaly in the trajectory of the interstellar visitor. A discovery that changes our understanding of what we are facing. Or nothing may happen. The sunspot may decay. The object may continue on its predicted path. December may pass without incident. And the convergence will be nothing more than coincidence. A statistical fluke that meant nothing. We cannot know which outcome awaits us. We can only watch and prepare and hope that the quiet continues. But somewhere in the back of our minds, we know that the quiet never lasts forever. Storms come. Events occur. The calm before is always followed by something else. December 19th approaches. The ancient traveler draws near. The wound on the sun still bleeds energy into space. And we wait in the quiet for whatever comes next. What the probes will see. The eyes turn toward 3I. Atlas represent the most sophisticated observation campaign ever assembled for an interstellar object. Dozens of instruments from multiple space agencies and ground-based observatories are gathering data that will take years to fully analyze. For a brief window in late 2025, the third visitor from beyond our solar system commands attention from the best equipment humanity has ever built. Let me walk through what we are deploying and what we hope to learn. The Hubble Space Telescope, launched in 1990 and still operating after more than 3 decades, offers resolution that ground-based telescopes struggle to match. Atmospheric turbulence blurs the view from Earth's surface. Hubble, orbiting above the atmosphere, sees with crystalline clarity. it can potentially resolve details of the coma structure, the distribution of dust around the nucleus, the geometry of any jets venting from the surface, and changes in brightness over time that might indicate rotation of an irregularly shaped body. The telescope has already captured images during the object's inbound journey, and additional observations are scheduled for the December closest approach. The James Webb Space Telescope, launched in 2021, extends our vision into the infrared. Heat radiates at wavelengths our eyes cannot see, but Webb can detect with exquisite sensitivity. For a comet-like object, infrared observations reveal the chemical composition of outgassing material water, carbon dioxide, carbon monoxide, and other volatiles each leave distinct spectral signatures. Webb has already confirmed that the coma of 3I, Atlas, is dominated by carbon dioxide rather than water. This is unusual for a comet from our solar system, where water ice typically drives activity. But for an object that has spent billions of years in the cold of interstellar space, the volatile inventory may be different. Carbon dioxide sublimates at lower temperatures than water, suggesting it might be the first material to become active as the object approaches the Sun. The infrared observations can also constrain the size and thermal properties of the nucleus. How much heat is the surface absorbing versus radiating? What is the albedo, the reflectivity of the surface? These parameters help distinguish between different compositional models. Ground-based telescopes contribute their own capabilities. The Very Large Telescope Array in Chile, the KEK Observatory in Hawaii, and the Gemini telescopes in both hemispheres have all turned their attention to 3I, Atlas, at various points in its journey. Spectroscopy from these facilities can detect specific molecular species in the coma with high precision. Of particular interest is the nickel-to-iron ratio measured in the outgassing material. As mentioned earlier, this ratio is unusually high for 3I, Atlas, compared to typical comets. Further observations may clarify whether this reflects the bulk composition of the nucleus or some surface phenomenon related to the interstellar environment. Beyond traditional observatories, a constellation of specialized missions are contributing data. The Parker Solar Probe, which passes closer to the Sun than any previous spacecraft, observed 3I, Atlas, during the perihelion passage from its unique vantage point. The probe is designed to study the solar corona and solar wind, but its instruments can also detect objects passing through its field of view. Any observations from Parker during the hidden window would be particularly valuable. The SOHO Satellite Solar and Heliospheric Observatory, which has been monitoring the Sun from the first Lagrange point since 1995, used its coronagraph's special instruments that block the direct light of the solar disk to reveal the faint corona to capture images of 3I, Atlas, as it passed behind the Sun. These images show the object brightening as it approached perihelion. Consistent with increased cometary activity from solar heating, the PUNCH mission, launched in 2024, is designed to study the connection between the solar corona and the heliosphere. Its instruments detected 3I, Atlas, in late October as the object neared perihelion. The data is still being analyzed. The European Space Agency's JUICE mission offers a unique opportunity. Originally launched to study Jupiter's icy moons, JUICE is currently in the cruise phase of its journey. By fortuitous timing, its trajectory brought it within 64 million km of 3I, Atlas, on November 4th, just days after perihelion. JUICE carries a suite of instruments not originally designed for cometary observation, but that can be adapted for the purpose. The Janus Visible Imager can capture high-resolution images. The MAGIS infrared spectrometer can analyze thermal emissions. The SWI submolecular wave instrument can detect certain molecules in the coma. The JUICE observations represent the first post-perihelion data from a close encounter with the object, with results expected in early 2026. These images may reveal details invisible to Earth-based telescopes, including any changes in the nucleus resulting from perihelion heating. Looking further ahead, NASA's Juno spacecraft at Jupiter will have an observation opportunity in March 2026. By then, 3I Atlas will be receding from the Sun, its activity diminishing as it cools. But any remaining outgassing should still be detectable. The trajectory data from Juno will further refine our understanding of the object's path. What are we looking for? At the most basic level, we want to characterize the object's size, shape, composition, rotation, and activity patterns. These parameters will tell us about the environment where 3I Atlas formed and the history of its journey through interstellar space. But we're also looking for anomalies. Any deviation from the expected trajectory would be significant. Comets often show non-gravitational acceleration due to outgassing. Jets of material from the surface push the nucleus like tiny rocket engines. This effect can be measured and modeled. If 3I Atlas shows acceleration that cannot be explained by observed outgassing, that would require further explanation. Oumuamua, the first interstellar object, displayed exactly such anomalous acceleration. The deviation was small but measurable. Several explanations were proposed, including outgassing of invisible volatiles, but none was fully satisfactory. The mystery of acceleration remains unresolved. Will 3I Atlas show similar anomalies? Preliminary data suggests the trajectory is consistent with gravitational physics, but the analysis is ongoing. Any deviation would immediately become the focus of intense investigation. We're also looking for secondary objects. If 3I Atlas released material during its perihelion passage, whether through natural fragmentation or hypothetical deployment, that material should become visible as it separates from the main nucleus. Tidal forces and radiation pressure would cause fragments to drift apart over time. By December, any significant separation should be detectable. So far, no confirmed fragments have been observed. The main body appears intact, but the surveys continue, and any new detections would be immediately reported. We are looking for spectral signatures that might indicate unusual chemistry. The nickel anomaly is already documented. Are there other unexpected features in the spectrum? Any absorption or emission lines that do not fit standard cometry models would attract attention. Even the absence of expected features could be informative. This is the essence of exploratory science. We have models that predict what a natural interstellar comet should look like. We compare observations to those models. Where they match, we learn about cometry physics. Where they differ, we learn something new. The data flowing back from all these instruments will take months to fully analyze. The December observations will provide the closest views we will ever have of 3I Atlas. After the closest approach, the object will begin to recede, growing fainter week by week until it is beyond the reach of even our most powerful telescopes. We have one chance to study this visitor in detail. The international astronomy community understands this. Resources have been allocated. Observation time has been scheduled. The data collection is underway. What the probes will see depends on what is there to be seen. If 3I Atlas is a natural comet, the observations will reveal the properties of an ancient icy body from another star system. We will learn about planet formation in distant environments. We will add to our understanding of the galaxy's chemical inventory. If 3I Atlas is something else, the observations might reveal anomalies that demand explanation, unexpected features, unexplained behavior, data that does not fit any natural model. We do not know which outcome awaits us. We can only point our instruments and gather the data. The probes are watching, the telescopes are recording, and in the data streams flowing from satellites and observatories around the world, the answer may already be written, waiting for us to read it. The analysis pipeline for cometry observations is well established, but 3I Atlas presents unique challenges. The object is moving fast, at over 100 miles per hour relative to the Sun. It crosses significant portions of the sky from night to night. Tracking it requires continuous updating of telescope pointing. The exposure times must be short enough to avoid motion blur, while still gathering enough light for meaningful analysis. The coma obscures the nucleus, unlike asteroids, which present bare surfaces to our instruments. Comets surround themselves with halos of gas and dust that scatter and absorb light. Determining the properties of the nucleus requires modeling and subtracting the coma's contribution, a process that introduces uncertainties. The distance is large, even at closest approach. 3I Atlas will be nearly 270 million km from Earth. At that distance, angular resolution is limited. Features that would be obvious on a nearby object become indistinguishable points of light. But the instruments are sophisticated, and the techniques have been refined over decades of comet observation. Spectroscopy provides the most detailed chemical information. By spreading the light from the coma into its component wavelengths, astronomers can identify the molecules present. Each species absorbs and emits light at characteristic frequencies, creating a fingerprint that can be read by sensitive instruments. 4. TRES-I Atlas. The spectroscopic data has already revealed the unusual nickel-to-iron ratio mentioned earlier. Further observations may clarify whether this reflects the bulk composition of the nucleus or a surface phenomenon. The answer could provide insights into where the object formed and the conditions that prevailed there. Photometry tracks brightness changes over time. If the nucleus is irregularly shaped, as most cometary nuclei are, its brightness will vary as different faces rotate toward the observer. The period of variation reveals the rotation rate. The amplitude of variation constrains the shape. For TRES-I Atlas, photometric observations have detected periodic brightness fluctuations that some have called a heartbeat. The period appears to be on the order of hours, consistent with a slowly rotating nucleus. Whether this represents natural rotation or something else remains to be determined. Astrometry measures position with extreme precision. By tracking the object against background stars, astronomers can refine the orbital parameters and detect any deviation from gravitational predictions. This is the technique that revealed the anomalous acceleration of Oumuamua. For TRES-I Atlas, astrometric monitoring is ongoing. The trajectory appears consistent with gravitational physics so far, but the critical observations will come in the weeks after closest approach, when any accumulated deviation would be most apparent. Polarimetry measures the orientation of light waves. When light scatters off particles, it becomes partially polarized. The degree and type of polarization provide information about particle size and composition. The extreme negative polarization of 3I Atlas is one of its documented anomalies, suggesting dust properties unlike any previously observed in comets. Each technique provides a piece of the puzzle. Together, they paint a portrait of the visitor that will be analyzed for years after it departs. The timeline is unforgiving. 3I Atlas will be at its brightest and closest for only a few weeks. After that, it will recede, fading against the background stars until it falls below our detection threshold forever. We have one chance to understand this object. The observation campaign represents the best effort humanity can muster. Whatever answers exist will be found in the data now being collected, or they will be lost to the interstellar void along with the object itself. The Fibonacci Whisper. In the weeks following the discovery of 3I Atlas, something remarkable happened on the internet. The usual flow of misinformation accelerated into a torrent. Claims multiplied, theories proliferated, and somewhere in the noise, a particular story began to circulate with viral intensity. The story claimed that 3I Atlas was emitting signals, not just any signals, but regular pulses at intervals of 147 seconds. The pulses supposedly contained numerical sequences, specifically the Fibonacci numbers, a series where each number is the sum of the two preceding it. The frequency was said to be 1,420 megahertzes. The hydrogen line, known in scientific circles as the most likely frequency for interstellar communication because it corresponds to the emission spectrum of neutral hydrogen. The story spread across social media platforms. It was picked up by tabloid websites. It was attributed to unnamed scientists, to leaked documents, to supposed intercepted communications. In some versions, the signals had been decoded to reveal messages: observe, prepare, understand, the gate awaits. None of this is confirmed. I want to be absolutely clear about the status of these claims. There are no peer-reviewed papers documenting signal detection from 3I, Atlas. There are no official announcements from observatories or space agencies confirming electromagnetic emissions of artificial origin. The stories circulating online do not cite sources that can be verified. This does not mean the stories have no basis. It means the basis cannot be confirmed. The physicist Michio Kaku was cited in some versions of the story, allegedly describing pulses that should not exist. But Kaku has not published any scientific paper on the subject, and the quotes attributed to him appear to originate from viral video content rather than academic sources. Avi Loeb has discussed what he calls the heartbeat of 3I, Atlas, referring to observed brightness variations that pulse at regular intervals. This is a real observation. Cometary nuclei often display periodic brightness changes as they rotate with different phases, presenting different reflectivity to observers. The period of variation can be measured, providing information about the rotation rate of the nucleus. But a rotating comet is not the same as an artificial signal. The psychology of why these claims spread is worth examining. We are a species that evolved to find patterns, even when none exist, faces in clouds, meaning in noise. Our brains are wired to connect dots, to see order where there may be none. It's part of our survival instinct, but it also means we sometimes create patterns where there are none. In this case, the idea that an interstellar object could be sending signals taps into an ancient and deeply rooted human fascination with the unknown, with the possibility that we are not alone in the universe. As much as the idea of alien messages captured our imagination, it is important to keep in mind that extraordinary claims require extraordinary evidence. Until the evidence is peer-reviewed and verified by credible sources, the claims of signals from 3I, Atlas, must remain speculative. That doesn't mean they're irrelevant, it just means we must keep our scientific integrity intact and approach these claims with the same skepticism we apply to any unverified assertion. What we are left with is a tantalizing mystery. 3I, Atlas, presents us with numerous anomalies, some of which challenge our understanding of comets and interstellar objects, its trajectory, its unusual composition, and its brightness fluctuations all suggest there is more to learn, more to discover. However, until we gather and analyze more data, all these possibilities remain within the realm of scientific curiosity, not conclusion. So, while the story of signals and Fibonacci numbers makes for compelling speculation, it is the data from the instruments, the observations from the telescopes, and the analysis from the scientific community that will ultimately guide us toward the truth. For now, we continue to watch, observe, and wait for the answers to unfold, one observation at a time. We're also a species that has spent decades imagining contact with extraterrestrial intelligence through science fiction, SETI programs, and speculation about our place in the cosmos. When an unusual object arrives from interstellar space, the template is already in place. We have been primed to expect visitors, and when the visitor displays anomalies, when its trajectory seems suspicious and its composition seems strange, the leap to artificial origin is almost irresistible for some minds. Approximately 40% of social media discussion about 3I, Atlas, invokes extraterrestrial intelligence in some form. This is not a fringe position. It is a substantial fraction of the public conversation. The desire for contact runs deep, but desire is not evidence. What would a genuine artificial signal look like? This question has occupied SETI researchers for decades. The challenge is distinguishing intentional communication from natural phenomena and from terrestrial interference. Natural sources can produce remarkably regular patterns. Pulses from rapidly rotating neutron stars emit radio energy at intervals as precise as atomic clocks. When pulsars were first detected in 1967, The regularity of their signals led to brief speculation about artificial origin. They were nicknamed LGM, Little Green Men, before the natural explanation was established. Artificial sources would presumably carry information. Random pulses are not communication. To qualify as a signal, there should be structure that encodes meaning. Mathematical sequences are often proposed as a universal language, since mathematics should be the same everywhere in the universe. The Fibonacci sequence, prime numbers, geometric ratios. These might serve as a calling card to prove artificial origin, but detecting information requires ruling out all natural and instrumental explanations first. This is difficult. Instruments have noise. Electronics produce spurious signals. Software has bugs. The history of SETI includes numerous false alarms where exciting detections turned out to have mundane explanations. The WOW signal of 1977 remains the most famous unexplained detection. A radio telescope in Ohio recorded a burst of intensity at the hydrogen line that lasted 72 seconds and has never been repeated. Despite decades of follow-up observations, the source has never been identified. It might have been a spacecraft transmission reflected from debris. It might have been a natural phenomenon not yet understood. It might have been equipment malfunction or something else entirely. The WOW signal demonstrates how difficult it is to confirm artificial origin. A single observation, no matter how striking, is not enough. Repeatability is essential. Independent verification is required. All alternative explanations must be ruled out. For tres eitlas, the bar is even higher. The object is moving. The geometry is changing. Any signal that might be detected one day might not be detectable the next, as the orientation changes. And the object will be observable for only a few more months before it recedes beyond our instrument's reach. The claims circulating online do not meet scientific standards. They are not supported by documented observations. They have not been verified by independent observers. They consist largely of screenshots, viral videos, and anonymous sources. But the claims reflect something real about human nature. We want there to be signals. We want the interstellar visitor to be meaningful. We want the universe to contain intelligence beyond our own. This desire is not irrational. The probability arguments that underlie the Fermi paradox suggest that intelligence should be common. The sheer number of stars, the abundance of planets, the long history of the galaxy all point toward a universe that should be teeming with life. Our failure to detect that life creates cognitive dissonance. Surely they must be out there. Surely we should have heard something by now. And so, when an interstellar object arrives, displaying anomalies that mainstream science cannot fully explain, the temptation to read it as contact becomes overwhelming for some observers. The viral claims are not evidence of signals. They are evidence of hope. Let me offer a framework for evaluating future claims. First, consider the source. Published peer-reviewed research is more reliable than anonymous social media posts. Named scientists speaking on the record are more reliable than quotes from viral videos. Official announcements from observatories and space agencies are more reliable than tabloid speculation. Second, consider the verification. Has the claimed observation been confirmed by independent observers using different equipment? A single detection could be instrumental error. Multiple independent detections are much harder to explain away. Third, consider alternative explanations. Have natural phenomena been ruled out? Have equipment malfunctions been investigated? Have terrestrial sources of interference been eliminated? The bar for claiming artificial origin is high, precisely because the implications are enormous. Fourth, consider the information content. Random noise is not a signal. Regular pulses could have natural explanations. Genuine communication would presumably carry structured information that could be decoded, not just rhythmic patterns. By these standards, the current claims about signals from 3I Atlas do not hold up. The observations that have been documented are consistent with natural cometary behavior. The viral claims have not been verified. The extraordinary evidence required for extraordinary claims has not been presented. This does not mean the claims are necessarily false. It means they have not been established as true. The distinction matters. 3I Atlas will continue to be observed in the coming weeks. If genuine signals are detected, they will be documented, verified, and announced through proper scientific channels. The world will know. Until then, the Fibonacci whisper remains just that, a whisper in the noise, a hope dressed as rumor, a desire for contact that runs ahead of the evidence. The history of SETI is a history of false hopes and dashed expectations. For over 60 years, radio telescopes have scanned the sky for signals of artificial origin. Billions of frequencies have been sampled. Billions of star systems have been surveyed. The result has been silence, broken only by occasional anomalies that could not be confirmed. The WOW signal remains the gold standard of unexplained detections. On August 15th, astronomer Jerry Eman was reviewing printouts from the Big Ear radio telescope at Ohio State University when he noticed something extraordinary. A strong signal at 1420 MHz. The hydrogen line had appeared briefly and then vanished. The intensity was far above background noise. The bandwidth was narrow, suggesting artificial origin. Eamon circled the reading and wrote, "Wow," in the margin. The follow-up observations found nothing. The signal has never been detected again despite decades of attempts. Explanations have been proposed, including a secret military satellite, a natural radio source, and interstellar hydrogen excited by a passing comet. None is fully satisfactory. More recently, the Breakthrough Listen project has conducted the most comprehensive SETI survey in history. Funded by technology entrepreneur Yuri Milner, the project has access to some of the world's largest radio telescopes. Millions of stars have been observed. The data analysis is ongoing. So far, no confirmed signals have been announced. The silence continues. But the absence of evidence is not evidence of absence. Our surveys cover only a tiny fraction of the electromagnetic spectrum. Our search strategies assume that alien civilizations would communicate in ways we can recognize. Our instruments have limited sensitivity. A civilization that wishes to remain hidden could easily do so. This is why the claims about 3I Atlas attract such attention. An interstellar object provides a different kind of contact opportunity. Not a signal traveling at the speed of light, but a physical artifact traveling at a mere fraction of that speed, something we can observe directly if we know what to look for. The claims circulating online represent a form of wishful thinking, a desire to find meaning in ambiguous data. But the underlying impulse is understandable. We have been waiting a long time for contact. The silence has grown heavy. When something unusual arrives from interstellar space, the hope that it might be meaningful is almost irresistible. Science requires that we resist that hope, at least until the evidence supports it. The burden of proof for extraordinary claims is high. The standards of evidence are rigorous. Feelings and desires do not constitute data. And yet the questions persist. 9 anomalies. A hidden window. A sunspot of historic proportions. A December convergence. The data does not support claims of artificial signals, but the data also does not rule out artificial origin. We are in a state of uncertainty where the natural explanation is more likely but not certain. This uncertainty may never be resolved. 3I Atlas will leave our solar system. It will not return. Whatever secrets it carries will depart with it, beyond the reach of our instruments, beyond the grasp of our understanding. We will be left with questions and probabilities, not answers and certainties. That is often the nature of science. The universe is not obligated to provide closure. The convergence. We stand now at the intersection of two trajectories. One has been traveling for 8,000 years, crossing the void between stars at speeds no human technology has ever achieved. The other emerged from the churning magnetic depths of our own sun, a wound on a familiar face that has appeared precisely as the visitor draws near. 3I Atlas will reach its closest approach to Earth on December 19th. AR4294 may return to the Earth facing the disk around Christmas. The convergence is not a collision. It is a coincidence of timing that invites questions we cannot answer but cannot ignore. Let me state clearly what we know. We know that 3I Atlas is an interstellar object, the third ever detected, moving through our solar system on a hyperbolic trajectory that will carry it back into the void from which it came. We know its path brought it within 5 degrees of the ecliptic plane, close to several planets, and to its closest approach to the Sun during a 2-week window when observation from Earth was impossible. We know the object displays 9 documented anomalies: unusual trajectory, unusual timing, unusual composition, unusual mass, unusual polarization, unusual survival, unusual color, unusual activity patterns, unusual in ways that cluster together around this single visitor. We know that the sunspot complex AR4294 through 4298 is one of the largest and most magnetically complex active regions of solar cycle 25. We know it appeared as the interstellar object emerged from behind the Sun. We know it is capable of producing X-class flares and potentially Carrington-class events. We know that a Carrington-class event in the modern world would be catastrophic power grids destroyed, satellites disabled, communications disrupted, an infrastructure dependent on electromagnetism brought to its knees by a magnetic storm. These things we know. What we do not know is whether they are connected. The scientific consensus holds that they are not. The Sun produces large sunspots during solar maximum. Interstellar objects follow gravitational trajectories without regard to solar activity. The timing is coincidence. The convergence is meaningless. This may be correct. It is probably correct. The natural explanation should be the default until and unless the evidence demands otherwise. But the evidence is ambiguous. The hidden window at perihelion means we cannot know what happened during the most dynamic phase of the object's journey. The object means that perihelion was the optimal moment for any propulsive action. The dark forest hypothesis means that a sufficiently advanced civilization might use natural-seeming phenomena to achieve its goals. We are speculating now. We've been speculating throughout this journey. Speculation is not science, but it is also not nothing. It is the exploration of possibility space, the mapping of what might be true before we have the data to determine what is true, and the possibilities are striking. If 3I Atlas is a natural comet, then December 2025 is a remarkable coincidence, an interstellar visitor and a historic sunspot converging on Earth by pure chance. The universe occasionally produces such alignments. They mean nothing. They signify nothing. They are the random clustering of events in a cosmos indifferent to human pattern seeking. If 3I Atlas is something else, the convergence takes on different meaning. A reconnaissance probe timing its closest approach to coincide with potential solar disruption. A weapon using our own sun against us. A test of our observational capabilities and our response to unusual events. I do not believe the second interpretation is correct. The evidence does not support it, but I also cannot prove it is wrong. The geometry prevents proof. The timing invites suspicion. The accumulated anomalies resist easy dismissal. What should we take from this? Perhaps humility. We have been spacefaring for less than 70 years. We have been aware of interstellar objects for less than 10. Our understanding of solar physics, of cometary behavior, of the possibilities for life in the universe, all of it is preliminary. We see through a glass darkly. As the ancient text says, we know in part, perhaps vigilance. The sunspot remains active. The threat of space weather is real. Regardless of any interstellar visitor, our infrastructure is vulnerable. Our preparations are inadequate. Whether or not December 2025 produces a major event, future Decembers will. The Carrington equation does not care about our readiness. Perhaps wonder. We live in a universe where objects from other star systems occasionally pass through our cosmic neighborhood. They carry information about environments we can never visit. chemistries we can only sample, histories that stretch back to before our sun existed. 3I, Atlas, formed 7 to 11 billion years ago in a stellar system that may itself have died long before Earth was born. We are witnessing a fragment of cosmic history, a messenger from the deep past. Perhaps gratitude. We have instruments capable of detecting these visitors. We have observatories that can track them across the solar system. We have space agencies willing to allocate resources for their study. A century ago, 3I, Atlas would have passed unnoticed. A millennium ago, its arrival would have been entirely invisible. We are the first generation of humans with the capacity to see what is coming. The convergence of December 2025 may be remembered as the moment when an interstellar visitor and a solar wound coincidentally aligned. A curiosity for future historians. A footnote in the long story of solar-terrestrial relations. Or it may be remembered as something else. We do not know which story we're living. We cannot read the chapter headings from inside the narrative. We can only observe and record and try to understand. 3I. Atlas will pass closest to Earth in less than 2 weeks. The sunspot will rotate out of view and may return for another pass. The data will continue to flow from observatories around the world. The analysis will continue for months and years. Whatever happens next, we will be watching. And now, as we draw toward the close of this journey, let me offer some final thoughts. The universe is vast. The silence between stars is deep. We send our signals outward and receive nothing in return. We build our detectors and strain for any hint of intelligence beyond our own. And still, the cosmos offers no reply. But occasionally something comes to us. Not a signal, not a message. Something physical, something real, an object from the void passing through our small corner of the galaxy, visible for a few months before vanishing back into the dark. These visitors do not answer our questions. They multiply them. They remind us how much we do not know, how vast our ignorance, how preliminary our understanding. 3I, Atlas, will leave our solar system. It will continue its journey into interstellar space. In a few thousand years, it will pass near another star. In a few million years, it will have crossed a significant portion of the galaxy. It carries with it whatever secrets it possesses, whether those secrets are the natural properties of an ancient comet or something stranger. We will not follow it. We do not have the technology. We can only watch it recede, growing fainter until it falls below our detection threshold and is gone. But we will remember. We will remember the July discovery. We will remember the autumn approach. We will remember the hidden window at perihelion. We will remember the sunspot that appeared. We will remember the December convergence, and we will wonder perhaps forever whether we understood what we were seeing. Thank you for joining me on this exploration. The questions we have raised tonight do not have easy answers. Perhaps they do not have answers at all. But the asking itself has value. The wonder itself is worthwhile. If you have found this content meaningful, please consider liking and subscribing. Your engagement helps these conversations reach others who share our curiosity about the cosmos. The universe is strange. The universe is beautiful. The universe keeps secrets we may never unlock. And tonight, as December unfolds and 2 trajectories continue their convergence on our small world, we add one more mystery to the collection. Sleep well, dream of stars, and remember that the darkness between them is not empty. Something is always passing through. In the grand scheme of cosmic time, our moment of observation is an infinite decimal. The universe has existed for nearly 14 billion years. Our species has been watching the sky with scientific instruments for less than 5 centuries. The window during which we could detect interstellar visitors is vanishingly small, and yet in this tiny window, we have now seen 3. Mua arrived in 2017. A tumbling object of unusual shape that accelerated away from the sun in ways we could not fully explain. It came and went before we understood what we were seeing, a blur at the edge of perception, raising questions that remain unanswered. Borisov followed in 2019, a more traditional comet with a tail and coma, offering less mystery. but confirming that interstellar visitors were not unique. Now, 3I Atlas passes through our cosmic neighborhood, larger than its predecessors, stranger in its properties, arriving during solar maximum with a trajectory that brings it closer to Earth than any interstellar object before. The frequency is notable, 3 objects in 8 years, when our detection capabilities were non-existent before 2017. Either we have become remarkably good at finding these visitors, or they are more common than we ever imagined. Or something else is happening. The natural explanation suggests that interstellar objects are abundant, numbering perhaps trillions within our solar system at any given moment. Most too small and dark to detect. We see only the largest and most active, the tip of an enormous iceberg. This explanation may be correct. It is consistent with our understanding of planetary formation and the ejection of debris into interstellar space. Every star system generates such debris. The galaxy should be awash in small bodies wandering between the stars. But the natural explanation does not account for all the anomalies. It does not explain why Oumuamua accelerated. It does not explain why 3I Atlas has such unusual chemistry. It does not explain the timing of the sunspot. Perhaps there is nothing to explain. Perhaps we're finding patterns in noise, seeing connections where none exist. The human mind evolved to detect threats, and it often detects threats that are not there. Or perhaps something is happening that we do not yet understand. The universe is vast and old. The possibilities for life are enormous. The silence of the cosmos may mean we are alone, or it may mean we are not listening correctly. Or it may mean something is listening to us. We do not know. We may never know. But we continue to watch because watching is what we do. It is why Richard Carrington built his observatory. It is why the Atlas telescope scans the sky night after night. It is why generations of scientists have devoted their lives to understanding the cosmos. The convergence of December 2025 may be nothing more than coincidence, or it may be the most important event in human history. We cannot tell the difference from inside the moment. We can only gather data, test hypotheses, and remain open to possibilities we have not yet imagined. The interstellar visitor continues its journey. The sunspot continues to rotate. The Earth continues to spin beneath both. Fragile and beautiful, home to the only intelligence we know for certain exists in the universe. Whatever comes next, we will face it together. And perhaps that is the most important lesson of all. The universe is vast and indifferent. Stars explode. Planets collide. Civilizations may rise and fall across billions of years without ever meeting. We are small and fragile, clinging to a thin layer of rock and water around an ordinary star in an unremarkable corner of a galaxy that itself is just one among hundreds of billions. But we are here. We are watching. We are asking questions. The interstellar visitor does not care about our curiosity. The sun does not care about our vulnerability. The physics of orbital mechanics and magnetic reconnection unfolds without regard for human hopes or fears. And still we watch. Still we wonder. Still we reach toward understanding, even knowing that understanding may forever elude us. This is who we are. This is what we do. This is why the questions matter even when the answers remain beyond our grasp. The convergence continues. The data accumulates. The mystery deepens or resolves. Time will tell which story we are living. Time will reveal whether December 2025 was coincidence or consequence. Until then, we watch the sky. We track the visitor. We monitor the sun. And we remember that the darkness between stars is not empty. It never was.